Hi, my name is Mia Benavides, and I will be presenting Part C of my group project on Avogadro's number. In early 1800s, Avogadro worked in a small lab with limited tools. He worked in a quiet space and has tools such as glassware, balances, and handwritten notes. He worked slowly on his experiments so he could reduce errors, since temperature and pressure are hard to control with limited tools in the 1800s. Avogadro's lab equipment was limited, as I mentioned, but he had things like glass tubes, flasks, thermometers, and balances to study gases. Every measurement had to be done by hand and recorded with a lot of care. Avogadro's compared gases under different conditions of temperature and pressure. He measured their volumes and observed how they combined in chemical reactions. From doing all of these experiments, he proposed that equal volume of gases contain equal number of molecules when measured at the same temperature and pressure. Avogadro had a lot of difficulties proving his idea because atoms and molecules were invisible and not yet really accepted by other scientists. Some of the safety issues he faced were working with gases such as hydrogen or oxygen. Working with these gases are risky because they are highly flammable and could go wrong very quickly if mixed incorrectly. Another safety risk, there was no ventilation systems like we have today or protective gear, so these experiments required tons of care and caution. The glass tubes and barometers used to measure gases were fragile and could often be inaccurate. Avogadro had to repeat experiments many times to get consistent data. All data had to be recorded and calculated by hand without any sort of calculators or computers. Avogadro spent hours analyzing results and checking for patterns in gas behavior. Any small math error meant redoing entire calculations. Avogadro wanted to understand how gases behaved when temperature and pressure changed. His goal was to explain why equal volumes of different gases reacted in predictable ways and to show that gas volume was related to the number of particles, not their type. The discovery was intentional. Avogadro designed his gas experiments on purpose to test his ideas about the relationship between gas volume and the number of molecules. His findings were meant to help chemists to understand the true nature of gases. The discovery made it possible to calculate molecular weights and balance chemical equations more accurately, benefiting future scientists in chemistry, physics, and engineering. Original benefits. Avogadro's gas experiments gave scientists a new way to understand the connection between gas volume and the number of particles inside it. His work helped explain why gases combine in simple ratios, which made chemical reactions easier to predict. Immediate advancements in the original field. His discovery advanced the study of chemistry by helping scientists calculate molecular weights and formulas more accurately. It became a key step in building the foundation for the atomic theory. Physics benefited from Avogadro's findings because they helped connect pressure, volume, and temperature in gases, leading to the development of the ideal gas law. Avogadro's work later influenced molecular biology and materials science by improving how scientists understand molecular structure and behavior at the microscopic level. Modern experiments are done now in much more advanced clean rooms and vibration-free work areas. These labs maintain strict temperature, humidity, and pressure control to prevent even the smallest measurement error. Researchers wear protective suits to keep dust and particles away from sensitive instruments. Scientists now use highly purified silicone 28 spheres instead of gases. Equipment includes X-rays and optical interferometers, high-precision vacuum balances, isotope analyzers, and laser systems to measure atomic spacing and mass. Computers are used to record and analyze millions of data points in real time, so no more handwritten things. Instead of measuring gases, scientists count atoms in a solid crystal to determine Avogadro's number. They grow and polish a 1 kilogram silicone 28 sphere, then use lasers and interferometers to measure the exact size and the spacing between atoms. From these values, they calculate how many atoms make up the entire sphere, linking the microscopic world to the macroscopic mole. Modern experiments use lasers, interferometers, and isotope analyzers to measure atomic structure with incredible precision. Technology now allows scientists to count atoms directly, something Avogadro could only imagine in the 1800s, which I'm sure he wished he had it in the 1800s. I would have wanted that. The silicone 28 sphere experiment has confirmed his law to an accuracy, helping redefine the mole in 2019. Researchers work in clean rooms that control temperature, pressure, and dust to avoid contamination. Protective suits, gloves, and air filtration systems keep the samples and the scientists safe. Equipment is sealed and calibrated regularly to prevent accidents or data errors. Modern information gathering, sensitive detectors, and lasers automatically record each measurement. Computers collecting data, temperature, mass, and lattice spacing hundreds of times per second, ensuring consistency across each trial. For modern information processing, powerful computers now analyze the data instantly, turning measurements into 3D models and precise calculations. These results are stored digitally, shared globally, and compared to standards maintained by organizations like NIST and the International Bureau of Weights and Measures. The silicone 28 sphere experiment provided a far more accurate way to define the mole and link atomic scale measurements to real-world quantities. This precision helps ensure that chemical formulas, material purity, and industrial measurements are all standardized worldwide. Other fields that benefit from this research are meteorology, physics, and chemistry. All rely on these results. Precise values of Avogadro's number improve atomic mass calculations, calibrate instruments, and support quantum research. Industries such as pharmaceuticals, nanotechnology, and semiconductor manufacturing also benefit from improved accuracy in mass and material measurement. Future goals for scientists. Scientists aim to measure atomic structure and constants with even greater precision. Future projects may use quantum technologies or improve silicone crystals to reduce measurement uncertainty and further confirm the relationship between atomic mass and the mole. Researchers are also exploring new ways to count atoms directly through quantum sensors and advanced imaging. Better accuracy in Avogadro's number will strengthen the foundation of measurements in science and engineering. It will improve the calibration of laboratory equipment, enhance material design at the atomic level, and support advances in nanotechnology, quantum computing, and medicine.
Process. Hello, today I will be talking about the original process. Joseph Loschmidt worked in mid to late 19th century Vienna and previously as a teacher in secondary school before obtaining a university position. His lab would have been relatively modest compared to modern labs. Early on, he used he used a small laboratory that the school allowed him to keep. A diffusion cell. As subscribed in his 1870 papers, two gases were initially separated by a horizontal partition in a vertical cylindrical container with the lighter gas on top. The partition was removed, the two gases were permitted to diffuse, and the fraction of mixing was carefully measured. His original difficulties. Working in the mid-19th century, Loschmidt operated in a time before modern chemical safety standards. His experiments on gases and possibly with reactive chemicals meant exposure to pressurized vessels or toxic vapors, risks that by today's standards would be required dedicated safeguards. In 1861, Loschmidt published Chemistry Studien I, which contained the first detailed structural diagrams of over 300 organic molecules, including benzene and ring compounds. Around 1865 to 1866, his goal shifted to qualifying matter at the microscopic level to estimate the diameter of molecules and the number of molecules per unit volume of gas. His original benefits. In his original field of chemistry and physical chemistry, Loschmidt's finding led to several important advancements. His structural diagrams directly influenced August Kelkuhl, Alexander Crum Brown, and other chemists who developed the modern system of drawing molecules. His calculation of molecular sign gave credibility to the kinetic theory of gases, showing the macroscopic properties like temperature and pressure can be explained through molecular motion. Modern labs rely on a combination of high-precision instruments and digital technologies that allow for accuracy, automation, and reproducibility. Modern experiments are highly structured, digitally documented, and often integrated with computational analysts. In contrast to Loschmidt's manual methods, modern procedures emphasize automation, safety, reducibility, and digital precision. Modern science has advanced tremendously since 19th century. Today's laboratories combine chemists, physics, biology, and computer science to explore matter at the atomic and molecular levels with incredible accuracy. The biggest advancements include the development of nanotechnology, quantum chemistry, artificial intelligence, and in research and automated experimentation. Scientific research does not remain confined to one discipline. Discoveries in one area often transform many others. For instance, physics research in quantum mechanism and electron magnetism has powered advancements in electronics, telecommunications, and computer technology. Chemical research contributes to medicine, agriculture, materials science, and energy storage, providing safer drugs, fertilizers, and batteries. Biological research benefits healthcare, food technology, and environmental conservation, improving crop yields and creating bio-based alternatives to plastic and fuels. Future expectations. The future goals for scientists focus on sustainability, health, energy, and space exploration. And understanding the fundamental nature of matter and life, one major goal is to develop clean and renewable energy systems that can fully replace fossil fuels. This generation batteries for large-scale energy storage. Another goal is to eliminate or cure major diseases through personalized medicine, gene therapy, and artificial intelligence-driven drug design. And that's all I have today.
Hello, my name is Giovanni Galvin. I'll be presenting Part C for the Avogadro's number project. So we got the original process. The original lab environment and parents' experiments were done in a quiet lab with glass containers and controlled lighting and absorbed tiny particles and liquids. Original lab equipment used microscopes, glass cells, and liquids with suspended particles, colloids, to study Brownian motion. The original experimental procedure prepared liquids with tiny particles, observed particles moving under a microscope, and measured particles movements. Next, we have original difficulties. Initial hurdles: observing tiny particles was very hard because they move randomly and they're difficult to track. And for the safety issues, we have handling liquids and glass equipment could cause spills or breakage, which was risky. And for equipment issues, early microscopes were not very precise, making it challenging to measure particle movement accurately. And for the last part, we have information procedure issues. Calculating Avogadro's number required long, detailed manual measurements and complex math, which was time-consuming and prone to errors. Next, we have the original motivation. The original motivation for the scientist Jim Perrin wanted to prove the existence of atoms and determine Avogadro's number. This discovery was intentional and not accidental, and the expected beneficiaries, scientists, chemists, and educators, were expected to benefit by gaining a better understanding of atomic theory and molecular of science. Next, we have the original benefits. Immediate benefits: Perrin work confirmed the existence of atoms, giving scientists strong proof of atomic theory. Immediate advancements: in the original field, physics, chemistry, scientists could now calculate Avogadro's number accurately and understand particle behaviors. In other fields, chemistry and biology, helped chemists understand molecular reactions and helped biologists study cells and molecules. In brand new fields, nanotechnology and material science laid the foundation for future research of microscopic particles and new materials. Next up, we have modern differences. We have modern advancements. Modern labs use digital microscopes, automated particle trackers, and computer simulations for faster and more accurate results. We also have modern protection and safety. Labs follow strict safety rules, use gloves, goggles, and equipment with built-in safety features to prevent accidents. We also have modern information gathering. Data is collected with sensors, cameras, and software instead of manual observation. We also have modern information processing. Modern information processing. Computers quickly analyze large amounts of data, reducing errors and giving detailed results in less time. Next, we have modern benefits. Modern benefits in research. Perrin works on Brownian motion and atoms, help scientists understand tiny particles, which is basis for modern physics, chemistry, and nanotechnology. Other fields this benefits: chemistry, biology, material science, and nanotechnology. Examples of technology spawned: nanomedicine, microelectronics and sensors, advanced materials for batteries and electronics, particle tracking, and imaging technologies. We have future expectations, future goals for scientists: study atoms and molecules in more detail, create better tools to see atomic motion, use atomic science to improve energy and materials, and potential benefits: new clean energy sources, stronger, smarter materials, and better medicine and tech advances.